Hello. Welcome to our Friday morning module wrap up. Today we're going to be going through some of the answers of some of the activities like some of these structures and as well as the properties of organic molecules. I know a lot of you had good questions throughout the week on this stuff. Thank you for asking. Hopefully I've been able to answer your questions. If you have more this morning, please join in. Let me know what you want me to talk about. Let me know what's giving you trouble, and we can spend some more time on that. As with our usual Friday at the end of a module sessions, I won't be introducing anything new today. We'll just be wrapping up from the week. All right, so with that said, I guess let's get started on the structures first. So last week we looked at how to draw these types of structures, and your homework was to complete these structures, and I'm excited to see your structures in Blackboard. I do want to go through some of the answers here. I'm not going to go through every one. I know we did, I think, one or two in class, but just to give you a sense of how to do these, and if you have your stuff with you, take it out, take a look at what you've written, and see if it matches up. It's a good way to be able to tell if you're on the right track or not. All right, so let's start with one of these where the Lewis structure is shown first. These are probably the easiest because you already have the Lewis structure. So all you have to do is convert that into a line structure. And you can really kind of keep the same geometry. So we could even imagine, like, you could take a pen with a contrasting color and just draw the lines between the carbons here. Oops, that's not a very contrasting color. Let me change that. Okay. So something like this, just to kind of get a sense of what this thing looks like on a skeletal structure level. You have something like that. Now, of course, we have to make the bends so that we can actually see the different carbon atoms. You could draw little dots or something there just to remind yourself that that's where the carbon atoms are. If this method isn't helpful for you and you just kind of see it as a zigzag, do what works for you. So I can kind of see this. I can number the carbons if I want to make sure I've kept track of everything. However I want to do that. And then all that needs to happen is to just kind of twist the angles a little bit to get a line structure. So if I were to do that just right next to here, I'd have like 1, 2, and 3. I'd make kind of like that. So instead of an L or a backwards L, I'd zigzag them to the correct angles. And then coming out here to 4, 5, and then 6, 7, and 8 are all coming off of 5. So I need like 3 more there. So you'd have something like that. And then as you draw these structures, it's always a good idea to renumber them. Just make sure that everything is accounted for. And you have something like that. All right. With these other two, same idea. The important thing here is to recognize that there are non-carbon and hydrogen atoms. So there's oxygen here and here, and those need to be basically left alone. So we don't cut the hydrogens off the oxygens. So something like this one over here would be a 3-carbon chain, and you can keep it in the vertical orientation or you can turn it on its side, whatever you prefer there. Let's say we do something like this. So here's our 3 carbons, 1, 2, 3, 1, 2, 3. And we're not going to show the hydrogens on the carbons in a line structure, but we are still going to show the oxygen, the OHs, both the oxygen and the hydrogen that's there. So angle-wise, it doesn't really matter where you put these. Remember, we like to kind of stretch these structures out as much as we can generally. So we might put the first OH up there and the second one over to the left and the third one down there to keep that nice stretched out form. If you put the OHs going straight to the right, that's fine too. The middle one really should not go to the right because we talked about that last time. You don't want to kind of cut this angle in half. You want to keep that nice broad angle and keep these sort of like triangular type angles intact. But the other two can go wherever. And if you do put the OH here, it's not wrong. It's not as nice looking of a structure, But the most important thing is that things are connected in the correct way. So as long as everything's connected properly, that's really what's important here. All right, so these other ones, we are take an extra step because it's very difficult to just look at the condensed structure and automatically split that right out into the line structure. So it's easier if we first expand it into a condensed structure but with lines and then do the line structure. So like let's look at K here. So for K, what we're going to do is take a look at this structure and expand it first and then put it into a line structure. So what I see first here is this uh, 2 carbons in parentheses, and then there's 2 of those whole groups. So we're going to go take that whole thing taken twice. Like that. Sorry, it looks like I had a connection issue for a second here. Okay, so that taken twice, and then that's going to go down to the CH, and then the CH2, CH2, NH2. So those both are connected to the CH, which then goes to the CH2, CH2, NH2. I'll move that up so you can see it. So there's our like expanded version of the condensed structure. Okay. So now that we've got that, we can take that and put it into the line format. So when I'm looking at something like this, I might kind of start with this straight line just because it's the most obvious to me, but you could start on the left or you could start on the right, whatever works for you. And I would go, okay, 3 carbons there. So I'm going to go 1, 2, 3. Then the NH2 coming off the right. And remember that that has to be still shown, NH2. We can't abbreviate that. We don't just say N there. We keep that whole group there. And then I've got 2 groups of 2 more carbons coming off this one on the left. So 1, 2, and 1, 2. So something like that. And then again, just to check everything, we want to make sure we have all the right carbons here. Sorry. Okay. So 1, 2, 3, 4. Got those. 1, 2, 3, 4. Then the others are going to be 5, 6, and 7. And when you count these out, make sure to kind of look back and just everything should be connected in the same way. So 1 is connected to 2, 1 is connected to 2. 5 is connected to 2, 4, and 6. 5 is connected to 2, 4, and 6. 7 is connected to NH2 and 6. Yes, okay. So as long as everything's connected properly, you've got the right structure. And even if your angles look different, if it's twisted or something like that, you still have the structure. All right, so that's how we do that. Okay, and then I also want to look at this this last one, the biggest one, probably the hardest one, R. So let's put that one up at the top. And actually, in order so that we can still see it, I'm just going to delete this one. Too much, it doesn't want me to delete it. Again here. Okay, well, we got that one deleted at least. All right, so this is big. This is a big one. And that is, I understand that that can be daunting and scary looking. But if we just use the same techniques, we should be able to still find the structure. So we're going to just take it piece by piece and write each piece out as a condensed structure and then figure out how to make that into the line structure. So starting from the right here, we again have this group of things. So we've got a 3-carbon group that's taken 3 times. So by now we know how to do that. We've done that a few times. So that's going to look like CH3, CH2, CH2, and it's going to look like we have 3 of them. Right, so there's our 3 groups of 3. And then those are all connected to this next carbon here. And this is going to look a little weird in a condensed structure just because there's so much stuff, but we can express it kind of like this. And then we're just going to work our way from left to right and keep adding things that we see. So next to that C is an O, then a CH2, CH2, CH, double bonded to another CH. We're going to have to turn the corner here just because we're going to run out of room. Another CH2, another CH2, then an O, then a C, and then that last bit is CH2, CH3. I'll move this up so you can see it. And there's 3 of them again. So we got 3 more things coming off this last one. And ask questions if you're not sure where this stuff is coming from. But that's the structure. It's like too big to even have all on the screen where you can see it. I can try to move out of the way a little bit. But that's our condensed structure. And yeah, it would also be good to number all of these if you're working on it, or just look at the 2 structures and kind of line them up and go, okay, this one goes with this one goes with this. With these really big structures, the biggest concern or the biggest thing that sometimes goes wrong is just that you lose track and you don't count enough of the ones in the middle or something. So just kind of going back, looking at it and seeing what's there can really help you with that. All right, then we convert this into the line structure. And same thing, we need to keep track of everything. So I'm going to start with this carbon just because then we can stick those other things on the outside. So I'm going to go C and then to O and then CH2, CH2, CH, CH. Oh, what happened there? Sorry, let's try that again. O, CH2, CH2, CH, double bond to CH. There's my double bond. Then CH2, CH2, O, C, and then these 2 carbon groups coming off. So like something like that. Over on the left, we can't forget that. We do have to put these 3 carbon groups in here. So that's the carbon that's here. So let's put a little 1 here just so we know what we're talking about. That's carbon 1 right there. So we got to have 3 more carbons coming off 3 times. So there's the top one, let's say. And then the next one. And then the next one. Something like that. So that would be a line structure for that whole mess. And hopefully it's similar to what you got as you worked through this. If you were off a carbon or a couple or weren't sure what to do with those end groups, take a look at this, maybe go through it again. And so now you know how to draw those. All right, if you have other specific questions on any of these, let me know either now or on Discord or something, and I can show you. The quiz, if you haven't taken it yet, there is no drawing on the quiz because it's on Blackboard. So the quiz involves more like it's like multiple choice where which is the correct line structure for this thing. So the concept is still on the quiz, but you won't be actually drawing anything. All right, then let's move over to properties of organic molecules. And I want to go through the answers to some of these exercises near the end. So I'm going to assume that you've gone through the packet. As with the last module, I'm not grading question by question on this thing. The point is for this to help teach you the concepts, and then you can do them on the quiz and just understand them going forward when we have discussions and other activities. All right. So number two, start with number two. Number one is kind of talking about the thing above a little bit more. All right. So for number two, a hydrogen bond is usually depicted as a dotted or dashed or dotted line. Sorry, dashed or dotted line. And so the important thing here is understanding what is it that makes a hydrogen bond. Now, first off, the reason it's a dashed or dotted line is because we want to distinguish it from an actual internal covalent bond, those lines that actually hold atoms together. Remember, now we're not talking about those anymore. We're talking about intermolecular forces, so the attractions between them. Can we go over 2.5 L? Yes, for sure. So that's this one, right? Or is that a different question? Let me open up the thing. Oh, that's the earlier one. Yes. Okay. Let's take a look at that one. So 2.5 L is here. Okay. So I'm going to draw that. We'll go through it. So the structure looks like this. Right, that's yeah. And the question is oh, not L but I. Oh yeah, okay, that's a weird one. Yeah, let's take a look at that one. So that's this one over here. Sorry, my drawing's not as great here. That's about right though, isn't it? Let me redraw that. It's a little something weird is happening with my pen here today. Yeah, and so I think the question is probably like, how do you know what where the connections are? Because there's definitely some overlap here, right? So this is actually like a three-dimensional structure. So if you can imagine, this is like a 6-carbon ring around here, and then there's like an extra bridge connecting the two sides of it. So if we were to look down, like straight down that way at it, it would look like this. It would be like a 6-carbon ring with this like bridge coming across. That's this peak here would be like right there. So what's going on there is, so our carbons, this is all carbon and hydrogen. And our carbons are here, 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 and here. So we've got 7 carbons. And then to find the number of hydrogens, we need to go to each carbon and figure out how many hydrogens are on there. Oh no, it looks like I lost my connection again. Let's see if it comes back. Okay, I think I'm back. Give it a second to catch up. All right. So C7. So then what I'm going to do is just label all of the carbons. So we can go to each site. Okay, maybe we're back. Maybe it'll hold. Okay, well, we'll try again. So that's 2 carbons at each of these outer ones. So we'd have a carbon or a hydrogen here, 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 because we need, remember, four connections to each carbon. Same here, right? 1, 2 at each. And then this top one also, we'd say, okay, there's 2 connections coming from that carbon. So that means there needs to be 2 hydrogens. And then these spots here have 3 connections to each carbon. So that means there's 1 hydrogen coming off there. So if we count those all up, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would be C7H12. I think the trickiest part of this one is it's hard to tell, like, because this is clearly looks like an intersection, is that a carbon or not? And because of this weird 3-dimensional structure, it's not. So there's not a carbon there. There's just these, it's like a 6-carbon ring with this bridge across the top. So that's how you do I. I think my connection seems okay now, but you may be lagging behind because it had to catch up. I'm not sure about that. But hopefully it's still at least recording and you can catch up. All right. You can always leave more questions if you have them, and I'll go back. But for now, we were talking about hydrogen bonds. So with hydrogen bonds, one important thing is to recognize that they're not the same as covalent bonds. They're these intermolecular attractions. And they're between a hydrogen that's connected to an oxygen or a nitrogen, and then another oxygen or nitrogen atom on another molecule. So in this case, this one here is the correct designation because you've got the hydrogen connected to the oxygen that's actually bonded to the oxygen, and then that's attracted to this other oxygen over here. These others all have something wrong. So here's 2 hydrogens, that doesn't work. Here's a hydrogen connected to an oxygen through the intermolecular attraction, but that hydrogen is connected to a carbon, so that's not right either. And then same thing, 2 hydrogens, that's not how it works either. It's between the hydrogen and the oxygen. And the way to know that, or the way you would know that to be able to answer that, is carefully reading the description above in an earlier part of the activity here. In this information section, it explains really clearly what a hydrogen bond is. And so you can use that to figure that out. All right, and then 4 is basically the same thing. It just wants you to draw it. So now let's take a look at this part that we starred. This is what you are going to have to be able to do on the quiz, and just moving forward as an important application of this idea of intermolecular forces, is looking at groups of molecules and trying to figure out which would have the highest boiling point or the strongest forces. So boiling point, strongest intermolecular forces are always correlated. So we'll be using those languages, that language kind of back and forth there. So for A, we're looking at this group of 3 molecules, and we're trying to decide which would have the highest boiling point and why. So there are always 2 criteria that you use to figure this out. One is the type of intermolecular forces. Is it hydrogen bonding? Is it polar? Is it nonpolar? And then second, and it's important that it's in that order, second would be the size of the molecules. So if the molecules all have the same types of intermolecular forces, then we can look at the size. But if they have different types, the different types of forces are much more important. So for this first one, we have similar types of forces here in that they all have OH. But the one thing that's mainly different and importantly different is that this molecule on the right has 2 OHs, whereas the other 2 only have 1. So if you remember, the strength of those forces comes from those connections between the OH type groups, either on water molecules or on other types of molecules. So the more OHs there are, the more connections that can make, and the stronger those connections can be. So when we have more polar functional groups like this, more OHs, more ways of doing the hydrogen bonding, we can have higher boiling points. So the answer here is the third one, because of those 2 different OHs that can be much stronger. And just for what these things are, the one on the left is ethanol, the one in the middle is propanol, and the one on the right is ethylene glycol, which is almost like syrupy. It's quite a bit more viscous, and you can use it like in your car for antifreeze and stuff like that. So much higher boiling can withstand those radiator temperatures. All right, for the second one now we have 3 different types of functional groups. So we have this carbon double bond oxygen, which we learned earlier is called a ketone. We have an OH, and we have NH2. These all have representatives in the tables, but the point of this question is to not look up the information in the table and see if you can just figure it out. So the way we would think through this is comparing the different functional groups. We know from what we did earlier that OH type molecules have the strongest interactions, followed by NH molecules, and then followed by these where you can't have any hydrogen bonding. So this would be the highest boiling in the third row because of its stronger hydrogen bonding interactions. If you said that the NH2 one had stronger interactions, that's a good guess also, and that's fair, I think, to guess that. But generally, the OH type molecules are going to have stronger interactions. All right, looking at the third one, now we have this. In this case, they all have the same type of functional group. So they're all carbon-hydrogen-based molecules with one OH group. So in this case, we can now look at the size because everything else is the same. We can say, all right, well, they've got the same functional groups, the same types of intermolecular forces. So the middle one is the biggest. That's definitely going to have the strongest forces. Because this one, well, as we saw in the tables, within a category, as you add more carbon, you increase the boiling point. All right, and then the third one is a pretty straightforward case of different types of functional groups. So this one has an NH in it, which means it can do some hydrogen bonding, whereas the other two are only carbon and hydrogen. So we can expect and correctly expect that one is going to have the highest boiling point because of its ability to hydrogen bond. Same thing with E. We have 3 molecules that actually all have very similar formulas. They're almost going to be the same. In fact, the one on the left and the one on the right do have the same formula. The one in the middle is just missing a hydrogen. But so we can't compare those by size because they're all the same size. We want to look at the functional groups again. So this is an ether, this is a ketone, and this is an alcohol. And among those 3, we know the alcohol can have the highest boiling point because of its intermolecular forces, because it can hydrogen bond. These two can't hydrogen bond. They are polar, they have oxygens, but as you can check in the tables above, ketones and ethers are not going to have nearly as high of boiling points as alcohols because they can't do that hydrogen bonding. All right. So number 6 is a little bit different type of question. This type of question, I often see people kind of answering it wrong because they're missing an important clue. So let's take a look at this. Benzoate ion is very soluble in water, but benzoic acid is not. Based on this information, which species do you think has a larger dipole moment, benzoic acid or benzoate? So this one, the important thing about this question is it's sort of telling you some important information. It's not just saying, answer this question based on the structures. It's telling you something. So it's saying benzoate ion is very soluble in water, but benzoic acid is not. So we can use that information. They're telling us that. Let's not ignore that. What does it mean for something to be very soluble in water? Well, as we've seen in the previous tables and the rest of this activity, generally, things that are very soluble in water are very polar, and things that are not soluble in water are less polar. So that's really the answer to the question. We don't have to use our structure skills here. That's the fact that the structures are drawn there is interesting, but it doesn't actually help us answer the question. We already know very soluble in water means very polar, large dipole moment, and not soluble in water means not very polar, small dipole moment. So that tells us right there that the larger dipole moment has to be benzoate because that's the one that's soluble in water. And notice how the question is worded. Which species do you think has a larger dipole moment? Chemistry is sometimes weird, and there's lots of different things going on. So we may not be right there. Like that may not actually be the true physical answer, but based on the data we're given, that benzoate ion is soluble and benzoic acid is not, that's the best answer. That we think that benzoate should have a much higher dipole moment because it is soluble in water. Those generally go together. All right. So that's the material for this week. We talked about measurements, we talked about organic structures, and we talked about these intermolecular forces. Hopefully that's all sitting okay with you. Hopefully the quiz goes well. And I'm excited to see and read your new at-home experiment proposals so that you can get started next week. Next week is our 4th module, which is the last one before the midterm. So if you have any outstanding stuff that's not done from earlier weeks, please make sure you get that done. Then we will start our midterm, or our 5th module after that, which spring break interrupts. So we'll be well on the into the second half of our course and get a nice break for spring break. And yeah, I will see you on Monday evening at 7, talk about the new module. So in the meantime, get your stuff finished up today and have a nice weekend, and I'll see you then.